Here is a problem to be solved using that involves free falling motion and uniform motion. It's a typical free falling motion question, and we'll read it together. A rock is dropped from a sea cliff, and the sound of it striking the ocean is heard 3.2 seconds later. If the speed of sound is 340 meters per second, how high is the cliff? All right, so we read the question. Remember, this is it involves from it's two parts. The first part is the rock. Uh, so I have two parts here. One is the rock uh, in free fall in motion, and two, the sound coming up. So this is going down, and two is a sound in uniform motion coming up. All right. So that's what we're going to use to find the height of the cliff. So let's visualize the question. Let's see what it looks like. So what we have is a cliff. All right. So first, from 1 to 2, we have a rock falling, right? So free falling motion. And then from 2 to 1 again, we have the sound going up. All right. So now that we've done that, let's see what is given to us, right? So we have two objects. We have the rock and we have the sound. And let's see what is that we know about that. So for the rock, it says it's being dropped. All right. So this is a keyword to tell us that the initial velocity is 0, right? And we don't know when it hits the bottom, but we know that it's in a free falling motion. So the acceleration is 9.8 meters per second squared. Now we have to make a choice, positive or negative. Since the rock is moving only down, we can choose down to be positive, right? So which means it's plus 9.8 meters per second squared. And that's all we know. So we know only two things actually about the free falling motion. Remember what I said about uniform accelerated motion, and free falling motion is one of them, that you have to know at least three things to be able to solve it, right? So let's see what we know for the sound. For the sound, we know that the speed is constant. It's 340 meters per second, all right? And for the sound, we can choose up to be positive just to keep it safe, right? So now let's see what is that we know about both of them, because pretty much this is what is given to us. Remember, is that time as well, right? So we have a time. It says that you hear the sound of the rock hitting the water 3.2 seconds later, which means 3.2 seconds later after you, from the moment you drop the rock, all right? So if I call delta t from 1 to 2, the time it takes the rock to hit the water, we don't know what it is. And delta t from 2 to 3, the time it took the sound to come up, we don't know what it is. However, what we know is that, let's put that one in the analysis, and I'm sure you know already, but, and also we are looking for this delta d from 1 to 2, right? Or delta d from 2 to 3, because they are technically the same, all right? So there you go. That's what it's given to us, and that's what we are required to find. So ultimately, we need to find that, all right? Everything else is an intermediate step. So let's do the analysis. So let's start with common sense, first of all. And it's given some time, right? Total time, let's write it here, which belongs to both of them. Delta D total is 3.2 seconds as verified. Yeah, it's 3.2 seconds. And you can see that everything has two significant digits. for our final answer. So let's start. First, we all agree that delta t total is delta t from 1 to 2 plus delta t from 2 to 3, which means those 3.2 seconds is the whole time it took the rock to hit the ocean at the bottom and for the sound to come up back to where you are, where you drop the rock, right? So that's one. The other thing is that delta d from 1 to 2 in magnitude is the same as delta d from 2 to 3, right? Whatever distance the rock had covered is the same distance the sound has to travel up, right? So let's just call it delta d to keep it simple, all right? Now we start writing some equations, okay? And so we found the link between, or the links between the rock and the sound, right? So now let's start doing some kinematics here. So for the sound, it's very simple. Delta d is the speed of the sound times the time of the sound, which is delta d from 2 to 3, right? And for the rock, we have delta d for the rock, remember, is the same, is initial velocity for the rock times the delta t from 1 to 2 plus half of the acceleration, which is g, times the time from 1 to 2 squared, right? But we already established that, so we're going to use those equation 1 and 2, right? We're going to use 1 and 2 because they are the same thing. Just we have to keep in mind that the direction of the velocities of the sound is opposite, okay? So first of all, both of them have delta. Let's write here, actually, this is delta d from 2 to 3, from 1 to 2. Since the left side is the same magnitude pretty much, what we can write here is that v times delta t from 2 to 3 is equal to, now initial velocity is 0, right? So it's just half of g times delta t from 1 to 2 squared. And here's our equation 5, right? Remember, vi is 0, so it was omitted, right? Now we can use also the relationship between the times, right? So we can write v times delta t total minus delta t from 1 to 2, right? So whatever 3.2 seconds minus whatever time it took the rock to travel down is equal to half of g delta t from 1 to 2 squared. So as you can notice now, there is only one unknown, all right, which is delta t from 1 to 2. And we do have a quadratic equation. So we can actually solve it. At this point, you could do the rearranging of the formulas and whatnot, or we can just plug in the numbers. It's up to us how we're going to do it. This I could do it by doing a full, complete solution without numbers and then plug in the numbers. But I'm sure that we don't want to do that right now. So let's put the numbers. So we have 340 times 3.2 minus 340 times delta t from 1 to 2 is equal to 4.9 delta t from 1 to 2 squared. So as you can see, it's a quadratic equation, right? So we have 4.9 delta t squared plus 340 delta t minus 340 times 3.2, 1088 is equal to 0, right? And we know how to use, we're going to use quadratic formula or whatever tools you have to solve a quadratic equation. We have delta t from 1 to 2 to be minus 340 plus or minus square root of 340 squared plus 4 times 4.9 times 1088. I remove the minus because 1088 has a minus in front of it. Divide by 9.82 times a, right? So we get delta t from 1 to 2. So let's try to do this quickly. 1088 times 4 times 4.9 plus 3.2 plus 340 squared. We get the time. My calculator is not working now. And once we get that, we can actually go ahead and find the distance route, right? So delta D is half of G delta T from 1 to 2. Sorry, that's not a vector. Delta T from 1 to 2 squared, and we sub it here, right? And then we get delta D. So this is a complicated question because it had more than one step. I'm not sure if we have something like this on the test, but it's a good way to practice. You have one on your practice questions on activity 3, I believe. All right. So again, that's how you solve a complex free-falling motion involving a combination of 2 or 3 equations. All right. Once I have a number, I'll post it also on a D2L should we need it.